So far, we have seen most of the forces that we will use in this course. In this video, we will examine the last major force, friction. To this day, friction remains a poorly understood force. If you wanted to win the Nobel Prize in physics, one way to do it would be to fundamentally improve our understanding of friction. To keep it simple though, we can say friction is a resistive force. It occurs when the grooves in rough surfaces interlock and chemical interactions occur between the atoms in each. We will use this animation to visualize friction. At first, the object is standing still. A small push doesn't move it. The push needs to be of a certain strength before the object starts moving. In this seemingly straightforward situation, there are in fact two different types of friction at work. We will look at both. The first type of friction is called static friction. Static friction is a force that prevents one object from sliding across another. It always opposes other forces and prevents motion. Here's the equation for it. As you probably guessed, static friction is a very unusual force. First, you probably noticed that lesser than or equal to sign. Unlike the weight force or the spring force, which have a defined value given by an equation, static friction does not have a defined value. It can change its value. In fact, it can take on any value up to a certain threshold. And the size of that threshold is given by the right side of this inequality. You probably noticed a second unusual thing. The n on the right side is our familiar normal force, but there's a newcomer here. That is the Greek letter mu sub s. It's called the coefficient of static friction. The coefficient of static friction is a number with no units. It tells you how slippery two surfaces are. It depends on the materials that are being used. Trying to push a wooden object on a wooden floor is harder than trying to push the same wooden object on ice. Every pair of materials has a unique coefficient of static friction, and several pairs are listed in a table in your textbook. The coefficient of static friction for wood on ice happens to be 0.1. For wood on rubber, it's 0.9. For wood on wood, it's 0.5. These values are measured or empirical. They are not easily derived. Let's apply this knowledge to this puzzle. You want to push a 150 kilogram wooden object across a rough wooden floor. What force must you apply before it starts moving? If you apply a force of 100 newtons, what would the free body diagram look like? What if you apply a force of 200 newtons? We start this question, as usual, by drawing a picture. Here is a 150 kilogram box, and you are pushing it along the floor. Now, the question was saying that this box experiences friction. And the question that we have to find out is, what is the limit of static friction? That is, what is the force that you have to apply to this box in order to start it moving? So now that we have our picture, let's list out all of the different forces that are acting on this box. Well, the two obvious ones are going to be the weight force down and the normal force up. But in addition to that, you also have the force of your push, which is an applied force, and the force that is opposing your push, the roughness with the floor. That is static friction. Now that we have this free body diagram, we can set our origin and axes. The origin is always set on the object, the spot in the free body diagram, And we can set our axes like so. I'm going to set rightwards as being my positive x direction and upwards as being my positive y direction. Now, let's do a force balance. We'll start with the y direction. In the y direction, the total force is given by the normal force up minus the weight force down, which I could write like this. And all of this is going to be equal to mass times acceleration in y. So we now have, I think I used to write it like this, normal plus negative weight force like that, but still. Normal force plus negative weight force is equal to mass times acceleration in y. Now, the object is not collapsing into the ground, and it's not levitating off of the ground. It isn't moving at all in the y direction. And so that means its acceleration in the y direction is 0. So normal minus weight must be equal to 0. You can put the absolute value sign, don't really have to. Okay, so what is the weight of this box? The weight of the box is given by mg. That's 150 times 9.81, which works out to 1471.5. So if the normal force minus the weight force is equal to 0, then that means that normal force minus normal force is equal to weight force, and so that the normal force is equal to 1471.5 J hat newtons. Now, let us solve for the force balance in the x direction. The total force in the x direction is given by the applied force pointed rightwards plus the force of static friction, which is pointed leftwards. I'll write it like this. We also know that according to Newton's second law, the total force must be equal to mass times acceleration. So that means that the applied force plus the negative static friction, again negative because it's pointed leftwards, is equal to mass times acceleration. Now, if we are just barely starting to get this box moving, then that means that the acceleration in the x direction is about as close to 0 as you can possibly get. For our purposes, we will say that it is 0. So simplifying all of this, we would end up with an applied force minus the force of static friction is equal to 0, which we can also write like this. The applied force is equal to the force of static friction. So now we just need to find out what is that threshold value of static friction at which acceleration just starts to exceed 0. So the force of static friction is given by this equation. We already worked out the normal force, and we can find the mu sub s, the coefficient of static friction, by looking in the book. For wood against wood, mu sub s happens to be equal to 0.5. And the normal force, as we worked out earlier, was 1471.5. So what this equation is now saying is that the maximum value of the friction force is going to be 0.5 times 1471.5. The friction force can take any value that is less than that, but it cannot take a value that's greater than this. This is the maximum possible value it can have. 0.5 times 1471.5 gives us 735.75. So that's the maximum value of the friction force, the static friction force. It can have any value up until 735.75, but not higher than that. And because the applied force, if you just want to start this moving, must be equal to the friction force, that means that the applied force must be equal to 735.75 I hat newtons in order for the force of static friction to be overcome. So in this question, we found the force of static friction, and more importantly, we found its threshold value of 735.75. That is the value that you need to apply in order to overcome the force of static friction. Now, suppose this wooden object is stationary and you push it with only 100 newtons of force. Because 100 newtons is lower than the threshold for static friction, the object is not going to move. The free body diagram would look like this. There would be the familiar weight force, normal force, and applied force. And we can deduce that there must be a static friction preventing any acceleration from rest. We can, if we want to be really rigorous, use Newton's second law to figure out that the static friction must have a size of 100 newtons. It has to exactly balance out the applied force. Now, suppose you push with 200 newtons of force. Because this is still under the threshold for static friction, the object still won't budge. But the free body diagram now looks like this, and we can calculate that the static friction must now be 200 newtons. The size of the static friction is capable of growing larger or smaller based on the sizes of other forces in order to prevent motion. If you push with 100 newtons, static friction increases to 100 newtons. If you push with 200 newtons of force, static friction increases to 200 newtons, and so forth. So far, we've looked at the first type of friction, static friction. Static friction only applies to stationary objects. There's another type of friction that applies to surfaces that are moving. It's called kinetic friction. Kinetic friction only applies to sliding objects, that is, objects that are moving across each other but which don't have wheels. The equation for kinetic friction is this. It's very similar to static friction, but while static friction has variable values, kinetic friction has a fixed value that depends on the normal force and this new parameter called mu sub k. As you probably guessed, mu sub k is the coefficient of kinetic friction, and it is only used for objects that are sliding past each other. For any pair of materials, the value of mu sub k is different and virtually always less than the value of mu sub s. As we saw before, for wood on wood, mu sub s was 0.5, but mu sub k is only 0.3. The difference arises because it is virtually always harder to start something moving than it is to keep something moving. It is virtually always the case that the coefficient of static friction, which you need to overcome to start something moving, is larger than the coefficient for kinetic friction, which you need to overcome to keep something moving. Consider this question. You push a 150 kilogram wooden object across a rough wooden floor with a force of 800 newtons. What is the acceleration? Notice that this puzzle implies the wooden box is already moving. In this question, we were told that we were pushing a 150 kilogram object across the floor. Now, something which is important over here is that we are already pushing it. This thing is already in motion, which means that it's going to be subject not to static friction, but rather to kinetic friction. So now let's draw the free body diagram. The familiar forces of weight and normal are still going to be there. You are pushing it across the floor, so there's going to be the applied force as well. And now there's going to be a force of kinetic friction, which is opposing that force which was applied. So at this point we can set our origin and axes. The origin always goes on the spot in the free body diagram. I will set rightwards as positive and upwards also as positive. Now, let's list all of the information that is known in the let's start with the y direction. I'll just keep one thing over here, which is that this object was being pushed with 800 newtons of force. That was the size of F sub A, the applied force. We'll hold that onto that for later. First, let's solve for the forces that are there in the y direction. The total force in the y direction is equal to the normal force plus the negative of the weight force. So this total force is equal to mass times acceleration in the y direction. So now we can combine these two and we can say that normal plus negative weight is equal to mass times acceleration. Now again, this object is not collapsing into the floor and it's not levitating off the floor. Its acceleration in the y direction is 0. So we can simplify this to say that the normal force minus the weight force is equal to 0, or equivalently, that the normal force must be equal to the weight force. All right, so now we need to calculate the weight force. The weight is equal to mass times gravity, which is equal to 150 times 9.81, which works out to 1471.5. By the way, if you're watching this video the whole way through, I'm fully aware that I did this just a moment ago, but the purpose of this is to show that every physics problem really should be approached as if it's a new question. That way you don't run the risk of making silly mistakes because you misread one thing and you decided to start halfway through a different question. So the weight force is 1471.5 newtons, J hat downwards, and the normal force is going to be the positive of that since it's pointed upwards. That would be 1471.5 J hat newtons. So this is now the normal force. And once again, we need the normal force because we want to solve for the kinetic friction. Now, let's proceed. In the x direction, the total force is going to be the applied force minus the force of kinetic friction. And that is in turn equal to mass times acceleration. So the applied force, we can simplify this to read minus the force of kinetic friction, is equal to
mass times acceleration. Now, one thing is different here. Here, we don't know that the acceleration is 0. We were told what the applied force is, but we haven't yet solved for what the kinetic friction is, so we don't know what the acceleration is. Therefore, let us solve for the kinetic friction. The size of the kinetic friction is given by mu sub k multiplied by the size of the normal force. Now, if you were to look in your textbook, you would see that mu sub k for wood against wood is 0.3 times a normal force of 1471.5. So now we can solve for F sub k. 441.45 newtons. Okay, so this gives us the force of kinetic friction. Let's plug in all the other information. The applied force was 800 newtons. And if we want to be really rigorous about it, we would say 800 I hat newtons. Minus F sub k, which is 441.45 I hat newtons. And all of this is equal to the mass, 150, times the acceleration, which is as yet unknown. So, 800 minus 441.45 is equal to 358.55. Divided by 150 is 2.39. So that's our acceleration. We could, I could write out this calculation a little bit more explicitly if you like. 358.55 I hat newtons equals 150 times acceleration. So acceleration is equal to 2.39 I hat meters per second squared.
All this can be summed up pretty easily. Static friction is the force that must be overcome to start something moving. Kinetic friction is the force that must be overcome to keep something moving. Since the coefficient of kinetic friction is almost always lower than the coefficient of static friction, the force of kinetic friction will correspondingly be lower than that of static friction. A typical puzzle asks what acceleration would result when the applied force overcomes static friction and the latter is subsequently replaced by the weaker force of kinetic friction. Consider this question. You push a 50-kilogram steel object on ice. What minimum force must you exert to get it moving? If you continue pushing with this force, what will its acceleration be?
In this question, we have a 50-kilogram steel object that is being pushed along the ground. Originally, it's actually standing still. It's not until later in the question that it gets pushed. And if it's standing still, that means it is experiencing static friction. After it gets moving, it'll be experiencing kinetic friction. So if we want to be rigorous about this, we actually should draw two different free body diagrams. So the first free body diagram would correspond to before the object starts moving. Normal force points up, weight force points down. The applied force, which is going to be needed to overcome the force of static friction, points right, and the actual force of static friction itself points left. I'm going to set origin and axes. Rightwards is positive, and upwards is positive. Now, let's solve for the force balance in the y direction first. The reason why we need to do this is because the force of static friction depends on the normal force. So we need to find out the value of the normal force before we can solve for the force of static friction in the x direction. So in the y direction, the total force is equal to normal minus, or I think the way I usually like to write it is plus the negative of weight. So, this, according to Newton's second law, must be equal to mass times acceleration. And so we end up with normal plus negative weight equals mass times acceleration. Now, this object is not collapsing into the ground, nor is it levitating off the ground. That means its acceleration in y is 0, because it's not moving in y. So we end up with normal plus negative weight is equal to 0, or normal force is equal to the size of the weight. The weight force is going to be equal to mass times gravity, at least the size of the weight force is, which is equal to 50 times 9.81, which works out to 490.5 newtons. So the weight force is 490.5 newtons. And that means that the normal force, since it's equal and opposite to the weight force, must be 490 newtons. The only difference being the weight force points in negative j and the normal force points in positive j. So this is the size of the normal force. Now let's take a look at the forces that are occurring in the x direction. The total force in the x direction is given by the applied force minus the force of static friction. Now, if we just want to find what is the threshold value of static friction at which this just about starts moving, then that means that once we have set the total force equal to mass times acceleration, that is applied force plus negative static friction is equal to mass times acceleration, then that means that the acceleration is going to be 0, because we're looking for the threshold value of static friction. Now let's actually go about and do that. The threshold value of static friction is given by mu sub s multiplied by the normal force. It just so happens that mu sub s for steel on ice is 0.4. The normal force is 490.5 newtons, like we saw just a moment ago. And now we just need to solve for the threshold force. 490 multiplied by 0.4 gives us 196.2. So that's the threshold value of the static friction. That's the maximum value it is allowed to take. So the applied force minus the static friction, the maximum value of the static friction is 196.2, must be equal to 0. So the applied force that you have to provide in order to start this thing moving must be 196.2 newtons, obviously. And since this is in the positive x direction, we should say I hat. In the second part of this question, we have started the steel box moving across the ice, and we want to find out what the acceleration would be. Now, what that means is we are no longer in the realm of static friction, because the box is already sliding. we're in the realm of kinetic friction. So if we want to be rigorous, we need to draw a new free body diagram. The weight force, it'll be the same as before, the normal force will be the same as before, and the applied force is the same as before. The only thing that's different is that we now have kinetic friction rather than static friction. And you'll notice that I drew this asymmetrically. I drew the kinetic friction as smaller than the applied force. There's a reason for that. In the earlier question, we said that the applied force and the static friction were the same size, but the kinetic friction is virtually always smaller than static friction for the same object, so I wanted to draw it smaller. We'll set our axes the same way as before, rightwards as positive x and upwards as positive y. Because nothing has really changed in the y direction, and this is a continuation of the same problem that didn't require a new picture, I'm not going to bother working out the y direction again. What I will find out is the acceleration that's taking place in the x direction. So, in the x direction, we now have a total force of applied plus negative kinetic friction. The total force is equal to mass times acceleration. So now, let's put these two pieces of information together. The applied force plus negative kinetic friction is equal to mass times acceleration. The applied force is the same as before, 196.2 newtons. But the kinetic friction is obviously going to be smaller than the static friction and also the applied force. So let's figure out how big that kinetic friction must be. The force of kinetic friction is equal to mu sub k, the coefficient of kinetic friction, multiplied by the normal force. Now, for steel on ice, mu sub k is 0.02. And the normal force was the same 490.5 newtons as it was before. So now we use this information to solve for F sub k. We'll use a calculator for this. 0.02 times 490.5, we get 9.81. Coincidence. The force of kinetic friction is 9.81 newtons. That's at least the size of that force. Now, what about the applied force? The applied force is the same as what it was before, 196.2 I hat newtons. The kinetic friction, which is pointing opposite that, is 9.81 I hat newtons, negative because it's pointing in the left direction. The mass of the object was 50, and the only unknown is the acceleration. So, 196.2 minus 9.81 is 186.39. Which is equal to 50 times acceleration. And then we divide the acceleration, we divide both sides by 50, and that gives us the acceleration. 3.73, let's call it. So this is the acceleration of the steel box along the ice. Now what happened in this question was you pushed with just enough force for this object to break past static friction. But once you did, static friction no longer applied, and instead you had kinetic friction, which is a weaker force than static friction. And so because the counter force that was opposing your applied force had diminished, you're going to get an acceleration that results.
You might also run into a question that gives you the acceleration of an object and then asks for one of the coefficients of friction. Here's an example. A truck is hauling a 10-kilogram box. When the truck accelerates at exactly 3 meters per second squared, the box flies off the bed. What is the coefficient of static friction between the box and the truck bed?
In this question, we have a truck and this truck has a 10-kilogram object in its bed. The 10-kilogram object is going to slide off the back of the truck. Now, what you might have guessed is that if it slides off, it's now in the realm of kinetic friction, which means that static friction was overcome. But when you think about it, that isn't all that obvious, is that? The thing is, the 10-kilogram object, if it had not slid off, it would have been moving with the truck. So the thing that has happened to this 10-kilogram object isn't so much that it wasn't moving. It's rather that it wasn't sliding against this truck bed. If it isn't sliding along the truck bed, then that means that it is still being held in place by static friction. But once it starts sliding, then that means that static friction has been overcome. This is actually a similar sort of situation to when someone whips a tablecloth off the table from under all of the cutlery and the silverware. The idea is that instead of looking for the point at which this starts sliding over a surface, we're looking for the point at which the surface starts sliding from under the object. Physically, it's the exact same question. The only difference is what is doing the moving. And because physically it's the same question, that means that we can approach it in exactly the same way. So we start off by drawing the free body diagram for the 10-kilogram object. It has a normal force, which had been pointing upwards, a weight force, which is pointing downwards. And here's where it gets interesting. The friction force would have initially been pulling it rightwards to move along with the truck. In this case, the friction force has just been overcome, but it would initially have been moving rightwards. Now, let's work out what the size of that friction force must be. I'm going to set rightwards as being positive and upwards as being positive. In the y direction, which we must always solve first in friction questions, the total force is going to be given by normal plus negative weight, as usual. Total force is equal to mass times acceleration. So normal plus negative weight equals mass times acceleration. Now, this object is not collapsing into the truck bed, nor is it levitating off the truck bed. That means that the acceleration is 0. So we now have normal force minus the weight force is equal to 0. How big is the weight force? It's equal to mass times gravity, which is equal to 10 times 9.81, which is equal to 98.1 newtons. And since normal force minus weight force is equal to 0, that means that the normal force must be equal to the size of the weight force, which is also going to be 98.1 newtons. And this would be pointed in the j-hat direction. So this is the normal force being exerted on the box by the truck bed. Now, let's revisit what was taking place in this question. If the box had stood still, that means that it would have accelerated with the truck, but it would not have been sliding on the track bed. And that means that the static friction would have been the force that was accelerating the box, because static friction applies as long as two surfaces are not sliding past each other. Now, for static friction to be overcome, we need to figure out what its maximum value would be. And the way that we do that is by solving for the total force that's taking place in the x direction. In the x direction, there is only one force, and that is the static friction. And since total force is equal to mass times acceleration, that means that the static friction was equal to the mass times acceleration. In this case, we were told that the mass was 10 kilograms, and the acceleration at which the static friction failed, the static friction was overcome, was 3 meters per second in the I-hat direction. That works out to 30 I-hat newtons. So that is the threshold value of the static friction. Now, if the threshold value of the static friction was 30 newtons, we can solve for what the coefficient of static friction is using this equation, the equation for static friction. So the threshold value was 30 I-hat newtons, and that is equal to the coefficient of static friction multiplied by the size of the normal force, which we found out a moment ago was 98.1 newtons. And since this is a scalar equation, I don't really need to bother with the I-hat or the j-hat. The last step then is to divide both sides by 98.1, and that's going to give me mu sub s. So 30 divided by 98.1 equals 0.306. So 0.306, that is the coefficient of static friction. And that is a measure of the slipperiness of these two surfaces between the 10 kilogram object and the truck bed. So if you accelerate at a rate that is high enough to exceed that, that force of static friction, the box is going to fly off. And that is precisely what happened in this question. Again, it works very similarly to how the dinite set with the plates and the cutlery is going to stay in place even if you whip away the tablecloth, provided you do it fast enough.
Needless to say, that truck driver then got cited for improperly secured load. In this video, we explored friction. In the next video, we'll explore more complex force puzzles that can still be solved with Newton's second law.